Hi, everybody. My name is Tahseen Rabbani. Today, I will be presenting practical and fast momentum-based power methods. My co-authors who are not here with us today are Jain, Arjun, Rajkumar, and Furong Huang. Before we begin, I'd like to thank the organizers of MSML 21 for allowing us to present at this virtual conference. So just an outline, we're going to review the classical power method, then go into an accelerated variant of it. Then we will introduce our algorithm, the Empower, and then we're going to advertise your paper and explain why you should read it after this presentation, because there are all sorts of good results in there that we're not covering in this presentation. Okay, so first let's go over the classical power method. So what is the goal? For a diagonalizable matrix A, we would like to compute its dominant eigenvalue, lambda sub 1, and its associated dominant eigenvector, b sub 1. So dominant here meaning the largest eigenvalue and complex modulus. So the power method is an iterative eigensolver which solves this problem, assuming there is a gap between the two largest eigenvalues. So their modulus has to be different, otherwise this won't converge. So let's go over this method. So assume A is an n by n diagonalizable matrix and assume this gap condition. So you start off with an initial vector q sub 0. You apply the matrix A to it at every stage, normalize, and then compute a Rayleigh quotient. So the q sub k's will be approximates of your dominant eigenvector. And by using these Rayleigh quotients, you're approximating the dominant eigenvalue. Okay, so this converges as long as your initial vector is non-orthogonal to v1. And as t goes to infinity, the q sub k's and the gamma sub k's will go to your dominant eigenvector, eigenvalue pair. All right. And the probability of selecting an initial eigenvector, which is orthogonal to your dominant eigenvector, is effectively 0. So it's a safe implementation. All right, so what's the convergence rate of this? It's t equals big O of 1 over delta times log of 1 over epsilon. So delta here is the eigengap, which represents the distance between lambda sub 1 and lambda sub 2. And epsilon here represents the L2 distance between your iterates, q sub k, or your final iterate, q sub big T, and your dominant eigenvector. Sometimes closeness, this epsilon measures closeness essentially. Sometimes closeness can be measured as a sine squared error, so the actual angular error between your iterates and the dominant eigenvector. So as you can see, as you enforce a tighter accuracy or closeness of estimate, the longer this algorithm will take. So Tahseen and his group introduced the accelerated stochastic power iteration, which is essentially a scheme for speeding up the classical power method. So it looks very similar to the classical power method, except in highlighted in red, we have this momentum-based subtraction. Okay, so essentially from your current iterate, you apply your matrix A as you subtract out the previous iterate weighted by this momentum coefficient beta. So to many of you, this should look familiar to accelerated gradient descent. So that's the scheme we're trying to imitate, and that's very heavily inspired from Polyak's heavy ball method. So the question is, does this work and how much faster is it? So if beta is set to this optimal value of lambda sub 2 squared over 4, then power plus m has a state-of-the-art convergence rate of big O of 1 over square root of delta times log of 1 over epsilon. So we've improved upon the classical power method convergence rate with this 1 over square root of delta. This is comparable to the state-of-the-art Lanczos algorithm convergence rate. So there's a caveat here. We can only achieve this state-of-the-art convergence rate if beta is set correctly to this lambda sub 2 squared over 4. However, we don't know what lambda sub 2 is at all at runtime. We're running an eigensolver to begin with to approximate the first eigenvalue. And once we have the first eigenvalue, maybe we can get the second eigenvalue, but we have no idea what any of the eigenvalues are at runtime. So we like the convergence rate, but as it is, it's not too practical. So what's our solution here? We would like to intelligently approximate lambda sub 2 and adaptively update beta at every iteration accordingly. So how do we approximate lambda sub 2? We're going to use what's known as a hot-link deflation, which approximates the second eigenvalue using the first dominant eigenvalue. Okay, So we're going to quickly go over this algorithm. So all we require is lambda sub 1, coarser matrix A, and then the dominant eigenvector V sub 1. So it looks very similar to a classical power method. It's just instead of running on A itself, instead the power method proceeds with this matrix, which is referred to as a deflation matrix. So we're just subtracting out lambda sub 1, V sub 1, V sub 1 transpose from A, which is why it's called a deflation matrix, because we're subtracting this out. And what this does is it shifts down the spectrum of A. So essentially, if you run a power method on this deflated matrix, the dominant eigenvalue of this deflated matrix that's going to come out will be lambda sub 2. Okay? So as your iterates go off to infinity, the W sub k's and the pi sub k's will converge to your second dominant eigenvalue eigenvector pair. Okay? So using this idea, we're going to approximate lambda sub 2 to form beta coefficients that actually will perform well. Okay? So now we're going to discuss our contribution, which we call DM power, which stands for delayed momentum power method. So it's broken up into two phases, the pre-M, pre-momentum phase, and the M phase, which is the momentum phase. Okay, so we're going to discuss the pre-M phase first. Okay, so what happens first looks very similar to a classical power method. We run the classical power method on A, and then as you can see here, we are acquiring basically approximates of the dominant eigenvalue eigenvector pair. Okay? So we have approximates of the dominant eigenvalue eigenvector pair. And then we use these approximations to run an inexact Hotling deflation. Okay, so the rest of this looks very similar to the Hotling deflation algorithm, but it's inexact, right? Because normally P here in a true Hotling deflation should be lambda sub 1, V sub 1, V sub 1 transpose. Instead, we're approximating that deflation component. Okay, instead we're using an approximation of lambda sub 1 and an approximation of, an approximation of lambda sub 1 and an approximation of V sub 1. So this is why we call this an inexact Hotling deflation. Okay, by using this inexact deflation, we are gradually approximating the second dominant eigenvalue and the second dominant eigenvector. So this W sub j, we hope will go towards V sub 2, which is the second dominant eigenvector in this mu sub j should go over to lambda sub 2. Okay, and then after big J iterations of the pre-M phase, we're going to move on to the M phase, which stands for the momentum phase. So this lambda sub 2 hat is going to be our best approximation of lambda sub 2. Okay, and then since it's our best approximation in lambda sub 2, we set beta over to lambda sub 2 hat squared over 4. So this isn't exactly lambda sub 2 squared over 4, which is our ideal momentum coefficient, but it's an approximation of it. And the rest of this proceeds as a standard power plus M implementation. So now we're going to experience acceleration because now we have selected a beta which actually lives within a convergent interval, or which should at least be close to our optimal assignment, which is lambda sub 2 squared over 4. Okay, so in this phase, it just looks like power plus M, and we're experiencing acceleration. At the very end, Q sub big K and mu sub big K, or nu sub big K are going to be our best guess, or not guess, approximation of a dominant eigenvector eigenvalue pair. Okay? So finer point here is in our meta algorithm that we've just gone over. The pre-M phase terminates after big J iterations, but we don't want to just leave after an arbitrarily selected number of iterations. We would want to exit that phase once we believe that our mu sub j's are close, or our current mu sub j is close enough to lambda sub 2, right? Because as we stated before, if beta is far off from lambda sub 2 squared over 4, then we are going to experience slow convergence or possible non-convergence. Therefore, in actual implementation, we're going to set a hyperparameter rho, which determines when to exit the pre-M phase. So specifically, our pre-M phase exits once our approximates of lambda sub 2 are close enough to each other, which is very common to classical or power methods and variants of them. We usually exit once our iterates are close enough. So you might ask, well, this is another hyperparameter. How much less restrictive is this than the original power plus M implementation? Well, it's far less restrictive than the original power plus M implementation because right now, because in DM power, all we are asking users to supply is a lower bound on the eigengap, not a guess of any eigenvalue itself or where they live along an interval, the interval being your full spectrum, but instead, how far away do you think the first and second eigenvalue are away from each other? So in our paper, we actually provide a convergence guarantee if you have an a priori lower bound on this gap. So if you wanted to be extra conservative, you go ahead and set this expectation of your lower bound on that gap to machine precision if you wanted to be absolutely sure or close to absolutely sure. Okay, so this is a far less restrictive hyperparameter. So informally, we have a convergence result. So with high probability, a proposed practical DM power after an efficient pre-M phase outputs an epsilon close estimate of the leading eigenvector within the state-of-the-art convergence rate, okay? Because after pre-M phase, we're basically moving to a power plus M phase, which should experience optimal convergence rates as long as beta is selected well. And due to the, well, we're hiding a bit of the details here, but with high probability, our beta is going to be close to that optimal value, which is lambda sub 2 squared over 4, okay? And we can do all of this without requiring any exact knowledge of what lambda sub 2 is or any hyperparameter which expects you to guess what lambda sub 2 is, okay? So just some results. We compare ourselves to other algorithms. So particularly we compare ourselves to the vanilla power method. Power plus M, which is running with perfect spectral knowledge. So this is the unreleased realistic scenario. We're using an oracle, which is running power plus M perfectly. So it's set beta to lambda sub 2 squared over 4. And we can do this because we're just experimenting with synthetic matrices and we know what the spectrum is exactly. So on the x-axis here, we have the x-axis represents epsilon. So how close we would like our output to be to the actual eigenvector, which we know because they're synthetic matrices. And then the y-axis measures how many iterations, so how many loops it takes to get to that level of epsilon closeness, okay? So we're already performing far better, DM power performs far better than the vanilla method. And as the eigengaps get tighter, it actually becomes competitive against the unrealistic, perfectly performing power plus M and the state-of-the-art Lanczos algorithm, okay? Especially as the eigengaps get tighter, our GM power performs better. And then rho here, like I said, you can set rho according to your a priori lower bound and how big that gap is. For these experiments, we have just set rho as a function of epsilon, which is how close you want your iterates to be in your estimation of the dominant eigenvector. So we just set rho as functions of epsilon, okay? But in practice, this doesn't have any particular significance. We just wanted to vary our rho selection and just demonstrate how they perform. And we're pretty flexible on how loosely we can set rho, okay, and still converge. All right, so what else is in the paper? We have a streaming version of DM power. So essentially imagine you have a large covariance matrix and you don't want to run any power method on it directly. You can go ahead and sample some columns and form a covariance matrix out of this sampled set. So we have a streaming version which corresponds to that setting, which does converge and performs very well. We also describe a machine learning application, which is spectral clustering. Basically, spectral clustering is just data separation. So we'd like to classify points into their natural geometric clusters. We also compare the number of pre-M iterations versus M iterations, because you might be wondering, well, we don't want to stay in the pre-M phase for too long because we're essentially concurrently running 2 power methods, which is a little expensive, but we show that the pre-M phase does not last that long. So essentially, we're not expending too much computational energy trying to approximate lambda sub 2. And then we also conduct extensive wall time and iteration complexity comparisons between ourselves, perfectly performing power plus M, vanilla, Lanczos, and other variations. Okay, so that's it. Can't wait to discuss our results with you folks at the actual conference. Thank you.